Okay. I would like to thank you all for inviting me to share some of the research that we have done. I'm very glad that I can connect with the students. That's more important, that the main purpose of accepting this invitation is to motivate the students to pursue their career in science, particularly in chemistry. So today I will be sharing some of our research, the work that we have done but some time back, not recently. That is basically on the functional materials and molecular assemblies for electrochemical or chemical sensing of bioanalytes, or what I say is the clinical metabolites, and water contaminants. So as I go through, you will be able to understand that what I mean these bioanalytes and water contaminants. I hope I am audible. Am I audible?
Yes, sir.
Okay. So basically, I am basically here. You can see in the map, right, West Bengal. That is here in the. There's a district of Midinapur. There is our campuses here. This is for those who are not familiar with the campus. And this is our IIT Kharagpur campus, and this is a bird view of our the building. And basically, our campus is a social retention center during the World War. That's why you can see here the bondage to freedom, the nation's journey. So that has been converted into Indian Institute of Technology, the first IIT in India. So let me show, this is my group members. Usually I show my students first because they are the soldiers in my group, and the funding agency from SCRB and CSIR and IIT Kharagpur. So basically this is the outline of my talk. I will briefly be explaining you about the material library that we have been working in the area of materials and synthesize different kind of material. And then the beauty of electrochemistry, and then I will briefly mention about the biosensor and so on. So this is basically, this is a group work. I mean the information about my group, that we work in the different area. The functional material I have enlisted here, and a couple of slides also you will be able to see that. We mainly work on the electrochemistry of functional material. And we earlier worked in the area of the sensing and biosensing. We continue to work on. Recently, our focus is shifted to the energy storage and conversion that I will not be sharing with you today. So you can see here the spectrum of the gallery of materials that we have synthesized since the early 2000. And I call this as a material library because we synthesize and look at the catalytic or the application of this material for various purposes. So this is another slide that shows you the different material that we have synthesized for various applications. So this slide, what we have here is that what I call is the pillars of electrochemistry. Those who can recall your fundamental studies that you have started from your class 11, 12, particularly I'm talking with the students. I hope students are there. So you start with your, at least you should remember the Nernst, and then Galvani, Volto, Davy, and so on. And then you'll be here Faraday. At least you can recall the Faraday's law, the Faraday's electrolysis, and then Daniel Cell and Robert Bunsen, and so on. So these are all, I consider them as the pillars of electrochemistry. Without their contribution, today we will not be able to talk about. Our textbook may not have a chapter of electrochemistry, whether in terms of physical chemistry or in terms of inorganic chemistry. So here what we have is that I briefly mentioned a fourth quadrant. I put is the beauty of electrochemistry. So what I have mentioned is that here is the electrochromic window. So this is basically, this is an aircraft which has the window of the aircraft is coated with a kind of a material. There electrochemistry come into picture, that you switch on the potential, you will be able to control the opaqueness or transparency of the your window. So that's why I call this as an electrochromic window. That is, you according to your requirement, you can do that. And then it's obvious that you have electroplating, that the one who have a fascination to have a gold-plated mobile phone or the award, the Oscar award. That's basically, there comes your electrochemistry. And this is quite common in the environment, the corrosion that we say that, but there's a typical electrochemical cell, that is the environment. We could see that. This again, I call this the beauty of electrochemistry. And then last not least, that we have what we have is the electroorganic synthesis. So you control the potential and do the electroorganic reaction to get your desired products. So with a brief mention, let me move on to that topic. That is what we have is the biosensor. I'm not sure how many of you are familiar with. The person I have put here, this is what we call the father of biosensor. I hope you are seriously listening to me. I'm spending 1 hour time just to reach out to students. It should not be like just for an attendance. I'm very seriously, talking to you, right? So online classes are, just log into the system, and then yeah. So it should not be the case. So I hope you get, at the end of my talk, you get something that for the improvement of your research career or your career in science, right? So here what we have is that, this is an image I put in, the father of biosensor, what we call the clock, 1918 to 2005. He's the one, for the first time developed. So you can read this IUPAC definition, what I actually mean by biosensor. So what I'm talking about is that when you step into the clinical laboratory, whenever you have a problem, that is, you have a sugar level or your cholesterol level, you step into the laboratory, they come up with this kind of a meter and a strip, and prick your finger and get up 1 drop of your blood and drop it in the strip and measure the analyte, whether it's the glucose or cholesterol or sodium level or potassium level. So what I am going to talk about is that how this strip is being made. So basically what we have here, what I call the transducer, that is nothing but of your conducting platform or transducing platform. There you have your biological recognition element. So when your substrate, say for example glucose, that comes into contact with your enzymes or what I call the biological recognition elements, that undergo a reaction, which is the signal is transduced to through the transducer to the electronic signal, and you get your digital value of your glucose or serum or the cholesterol, whatever it may be. So what I will be talking about is one kind of how do we fabricate this strip. It's a fundamental level, how we have attempted with the various metal. That is one aspect of that. I will be talking about the electrochemical as well as the optical signal, not necessarily for your bioanalyte, but also for the environmentally toxic and so the contaminants. So here I have given the development of biosensor. I'm not going to read it, right? How it is, 1916 it is started and how we developed. Now we have an advanced biosensor, including in your, you can have your app, mobile app. There you will be able to, measure your bioanalytes in your physiological fluids. So when we talk about the sensor or biosensor, what we need to look into this sensitivity, detection limit, and also on. You can go through it, and then what we have. The main importance is that the cost of the sensor is how much. How much is it cost? So basically, what we have, the low cost methods are preferable so that it can reach out the rural village. All the people can have access. So, as I said, you need to have stability and selectivity and response time. How do we modify that? What we need is that you can look at here a successful marriage between biological elements and the transducer is required for the development of biosensor. That is a key. The thumb rule is that this is a success. If you want to have a success in your sensing, your marriage between your transducer and your biological recognition element or chemical recognition element should be successful. Otherwise, you are in failure. So you can look at here. I have classified the biosensor into three different categories: first generation, second generation, and third generation. So what we have in the first generation, typically what we have is that very typical of the natural. In nature, what is happening? Oxygen is being converted into hydrogen peroxide or water. Substrate is converted into product. So here what we do is oxygen is converted to hydrogen peroxide by the when there's an enzyme. The substrate is converted into product. Say for example, you have a glucose which is getting converted into product, gluconic acid. In the presence of oxygen, which is oxygen is getting converted to hydrogen peroxide. Now you quantify the concentration of hydrogen peroxide. The enzymatically generated hydrogen peroxide is directly proportional to the concentration of your substrate, say for example your glucose. The second category also, instead of using oxygen, there are limitations there. You can use a mediator. Mediator is nothing but a redox molecule that shuttles the electron between your transducer and your redox center of the enzyme. So you don't need oxygen and hydrogen peroxide. You will be talking with the air diffusional mediator, a redox molecule. And the third category, I don't need oxygen, I don't need a redox mediator because each and every one has their own difficulty problems. So if I can directly wire the redox enzyme glucose oxidase to the transducer or the electrode, I can have if I can achieve the direct electrochemistry of this enzyme, I can quantify. So I will briefly mention about these three categories, and then I will move on to the others. So this diagram I will be coming. This is a very fundamental. Usually I don't put these are because the college students. I basically explain this is what we call the cyclic voltomogram. Basically, this is a current versus potential. This is a waveform. That is, I scan the potential from one end to other end, and I follow the current. This is what the signal I will be talking about. Right, the current that is generated is proportional to the concentration of the analyte. Okay, so let's start with the electrochemical sensing now. This is not a biosensing, it's electrochemical sensing. I'm not going to use any biological enzymes. I have simple chemical elements that I will be using. So you can read it here. What I have, the importance of why do we need to quantify or detect or sense the biological thiol. What are the biological thiol I'm talking about? Yeah, glutathione, that's a dipeptide, right? So then I have a cysteine and I have a homocysteine. These are representative examples. So the importance of sensing is written here. I'm not going to read it. And what is the detection limit? What is the normal level it is there? How we will be able to quantify. So it is quite challenging. By a simple method, you cannot quantify. So I will be explaining the electrochemical approach. How do I quantify? I mean, how do I detect the concentration of this thiol? So one method is the direct oxidation. You directly oxidize thiol that get converted into your dithiol, disulfide, and then you follow the current because you're oxidizing. But the problem is that you need a high overpotential, you need to spend more energy, and in the ill-defined voltomogram, you will not be able to quantify actual concentration. So basically, what is a reversible process, and it's a sluggish electron transfer. So another method what we have is the mediated electron transfer, the mediated oxidation or the catalytic oxidation. What do you have? You have a redox mediator, as I mentioned a couple of slides back. You start with the redox mediator, and then you do your electrochemical reaction. And the typical example is here. The black one is your redox mediator. That gives a reversible signature corresponding to the oxidation and reduction. And in the presence of your SH, that RSH, the current increases. This increased current is directly proportional to the concentration of your thiol. That is basically mediator is mediating or catalyzing the oxidation of your thiol to disulfide. And another method is there, you can derivatize. Right? You take a molecule and do the electrochemical reaction, it undergo a irreversible electrochemical reaction with the redox molecule that you have taken. That is again is an irreversible process. So you cannot cycle it back and forth, but if this method, here what we have, this can be cycled. The redox mediator can be cycled back and forth. That is an advantage of mediated oxidation. Let me give an example. So what I have, this is a very simple molecule. That is what I have, a catechol. This is a redox mediator that I'm talking about. It undergoes 2 electron, 2 proton redox reaction to give a quinone, orthoquinone. Now, there are 2 positions here which I can make use of it for the one for Michael addition reaction. So if I have a RSH or an SH thiol molecule, this I can subject this. If I generate this quinone in the presence of a thiol or a sulfide, that I can do a Michael addition at this any of this position and follow the concentration of my thiol. Suppose I have a substituted catechol, the I call it RCA or is a methyl or ethyl or anywhere with the alkyl group. Now I have one position here. I can do a Michael addition here. I can follow the electrochemistry of this molecule or this molecule to understand the concentration of thiol. Right, let me explain you. A little complex, little advanced topic. What we have is what we call the graphene and the graphene oxide. And I have a mercaptopropyl trimethoxysilane. Right. This is known to undergo hydrolysis and condensation. This is basically a BSc chemistry. Right. At BSc level, in the textbook level, you will learn that hydrolysis of silane and then condensation reaction. The same thing we do here in the presence of OH terminated, the graphene oxide. So at the end of the day, what I get is a complex architecture where I have a carbon network where I have a SH function with this SH terminated silane coupled with the carbon framework. So now I have a SH function. I'm going to use this thiol function for 2 different purposes. You can see here. So what I do is that this is architecture, a complex architecture. Now I want to immobilize on a transducer. So what I do is I take a gold electrode, and this gold has a fascination for thiol. It can go and simply adsorb on the gold surface and form a molecular assembly. Now I have a complex architecture. Now I assemble here on a gold surface. Now again, the other side of the architecture, what I have a multiple of plenty of your SH terminal is there. Now next step, what I do is that I do a NPH reduction in order to make this the carbon network conductive, because a lot of functional groups are there. The conjugations are broken, so I want to make this network as a conductive. So what I do is that I do NPH reduction. Simply, I get this architecture which is highly conductive and terminated with a SH function. Now what I'm going to do is I'm going to make use of the SH function to do a Michael addition. So what I do, I have a catechol or a substituted catechol, right? I mean, I do electrochemical cycling. Here I have. Now, once this is generated, this the quinone is generated. There are 2 positions available for Michael addition. The Michael addition with what? I have a SH function that can undergo Michael addition. Here I can attack, and then I will get a much complex architecture which has a catechol unit. This catechol unit is known to undergo reversible redox reaction. Okay, I need to come to the thiol. I'm making the step by step. I'm making the architecture or the platform for the sensing of my thiol. So just now you may ask that how do we make sure that this is undergo Michael addition reaction? Yeah, we follow what we call the electrochemical microbalance. How many number of RCA or how many number of CA can be calculated, right? Using the technique, what we call the piezoelectric effect. From this, you will be able to find out the number of molecules of CA, RCA that is covalently attached to this molecular architecture. So that's the electrochemical derivatization. The architecture is made. Now you have an architecture of this kind. Now this can undergo reversible redox reaction. That I mean electrochemically characterize it. right? I do have a characteristic signature for all that, how many number of molecules are there. You go with a different assembly and find it out. Here it is, I mean based on the data, it's considered to be a good one for the electrochemical sensing. So now what I do is that you can look at the scheme here. What I do here is I bring the thiol. Okay, this undergo a reversible redox reaction. This is nothing but of the previous architecture that I have given here. For simplicity, I have given simply a catechol and so undergo. Now I bring this SH function here, that is a thiol, that is my biological thiol, which undergo a Michael addition reaction here. This is what I call the derivatization. Yeah, irreversibly react. The second one, what I have here is a mediation. That is, this redox couple, I can cycle it again and again, and to generate, oxidize my thiol to my disulfide. So you have your voltammetric signature, mediation versus your derivatization. Right. Again, how do we find out whether it's really the thiol is going into attaching to electrode surface, whether it's a mediation or derivatization? If it is a mediation, there should not be any change in the mass. The catechol moiety cannot go and attach on the transducer. It is a simple mediation, simple catalysis. On the other hand, if it is a derivatization, what will happen? The SH, your SH function goes and covalently attached to the catechol here. As a result, the mass will change. So your voltammetric signal will be like this. You can see here frequency changes, that it tells there's a mass change. Here there is no frequency change. That means it's a mediation. Okay. Maybe it's a little complex, but advanced, but just I want to introduce that. So this is what we have, what we say is the flow injection. That is basically increase the sensitivity. You have a pump, you inject your sample, 10 microliter or 5 microliter, follow the current at a particular potential. This current is directly proportional to the concentration of the thiol that you have in experiment. Okay. So that's one part. There is a biological thiol. Second one is a water contaminant. What I have, I will be taking quickly mercury, arsenic, and chromium. First, let me start with the mercury. Right? It's a funny picture. Right? I mean, what we have, right? Well, I'm a tuna, right? There's a fish. It's a cartoon representation. Yeah, and you know, I'm dolphin free. That's a funny word. But other one says, baby, I'm loaded with methyl mercury. Right? There's a problem comes there. The mercury, how it is enter into the food chain, then you will be able to see here. Right? I'm not going to explain all this. It's a quite straightforward. To understand from the screen, as well as you should be knowing about that mercury contamination, how it goes there from the industry, and then drain, it goes by accumulation, and methylation takes place. And then what we have here, you have your seafood, and then you take it and then it contaminates. Right. So this is a quick, quick overview. What we have here, it starts from the water, phytoplankton and zooplankton and fish, and then predator, and then finally enter the food chain, and that by the human beings are contaminated or affected by the mercury. Right. This is one of the famous example. Minamoto Bay industrial mercury, a disaster happened. These are the real picture of the consequence of mercury contamination. That is in 1953 in Minamoto in Japan. That's a lesson that is learned in the beginning. So mercury to sensing, and so not only sensing, the removal is also important. You should remove it. The Environmental Protection Agency put a limit of maximum contamination limit up to microgram per liter. Right, that would be the maximum contamination in the drinking water. So whenever we do a sensing, or we need to validate with that one. So you can look at here. There is a couple of pictures. That is whatever I have shown here. It is in Japan. So these are the images that I have shown here is all up. From India, right? And then you will be able to see here the state where I live. this area, the red cone is contaminated, the groundwater is contaminated with very high amount of arsenic, not the mercury, it's the arsenic. Okay, this is the arsenic I'm talking about. Earlier when we talk about the mercury, this is about arsenic contamination. So you can see here what are the skin lesion, all other diseases are there. This is a prevalent where the people are drinking the groundwater contaminated with arsenic, where you have the red color region is more than 50 microgram per liter. So if you browse through the literature, there are plenty of methods are available. Usually, the biological molecules, yeah, your atoms or your fragment of DNA or DNA that you put it there, there's an interaction, and then you sense it by potential, electrochemically, or you can do by spectrophotometrically also. Widely, it has been electrochemical methods are used. There are plenty of reports are there. You need an expensive biological molecule, your aptamer or your DNA fragments or your other biological expensive molecules are required. So other methods are available to remove a highly porous network, what we call the metal organic framework or covalent organic framework, and so on. Plenty of it's available. So you can see here how the other methods are available. So I will be sharing you a very simple platform that is based on the silicate network. I mentioned that mercaptopropyl trimethoxysilane. So you have a nano architecture. I'm not going to explain this detail. Those who are interested, you can browse through the literature that I have, the references here and there I'm putting. So the basic idea is that you have a mercury 2 in solution, reduce to mercury 0, and then what you do is strip it back, oxidize it back, and then follow this current, right? The stripping current. That's what I have shown here, right? I initially deposit on this platform. This is my sensor platform. I deposit to 0, and then I strip the organization limits. Now what we have, right? If I can do this, the previous one, what I say, this is your mercury. And now what I have shown here is the arsenic. I do the arsenic. The same strategy I follow. I have an arsenic 3, deposit into arsenic 0, and follow the current using the same platform. Now, one of the problem in the actual real water is not talking about the lab water that's coming, real sample. You will have a large amount of your copper. So that's the interference. So copper, with this platform, we can detect both copper as well as your arsenic without any interference from each other. Now you bring the 3 analytes, your arsenic, your copper, and your mercury. So with a single platform, you can measure your arsenic, copper, and mercury with the what I have shown here. So this is the publication. Those who want to follow it, you can follow it, right? This is the limit of detection, that is 0.02 parts per billion. The platform is stable, quite stable. So how do we remove this mercury? Can we have any solution? Yeah, it's good that we can detect the mercury. Is it possible? So I will be showing, briefly sharing you the detection as well as removal using another platform. What I will be doing is that, as I have shown in the background, this is a porous material, right? The porous material, this slide shows how I detect the mercury using the carbon material, carbon-based material doped with sulfur. Okay, the rationally designed material. So we could get excellent selectivity, stable for a week. Limit of detection is 0.1 parts per billion with a signal to noise ratio of 14. Right? If you are not familiar, yeah, you need to browse through the literature, or you ask me later, I will be able to explain you what, or you can browse my literature, the publication. Okay, so this is a removal. That is what we do is that. This is the removal that we have. What's that? No, I did not get.
Yes, sir, we can proceed.
Okay. This is a cartridge kind of the apparatus that we fill this with the material, and then what we do, the separation, removal of the mercury, and then you have your different material. What you have is sulfur dope and so on. There are a number of cycles, 5 cycles. Yeah, you can comfortably you can make it. So this is another method that we have developed, the calorimetric sensing. You don't need electrochemical setup. It's a quite straightforward method for the sensing, not for the removal. So what we do is that we synthesize a silver nanoparticle and a galvanic displacement reaction based on this potential. Those who want to follow here, a galvanic displacement reaction between your silver nanoparticle and mercury 2+ ion. The color from this is the original color of your silver nanoparticle, which undergo galvanic displacement reaction with mercury 2+, and then you get your color changed. So limit of detection is 50 nanomole. Selectivity is highly selective. The reaction takes place with only with the mercury 2+. So if that is basically here we follow. This is the spectrophotometric method following it. Either you decrease in the absorption band here or increase in the band here. What we have is the longitudinal, the surface plasmon resonance, transverse and longitudinal, the component is here. So you will be able to quantitatively follow your the mercury concentration with the spectrophotometer. So this is another one that is there's a mercury. Again, the same platform that what I have mentioned earlier, that is the architecture, silicate network with the gold nanoparticle. Here we do with the chromium. Chromium is another contaminant, particularly the effluent from the leather industry or tannin industries that talk about. There we have a large contamination. As you know, that chromium 6 is carcinogenic. So we followed the method, and then we could detect the limit of detection as lowest concentration is 0.1 parts per billion, and it's quite pretty stable. And if you want, you can follow from this literature. Another one that is a quite recent one, what we have done is carbon-based material, right? Very simple carbon-based material, porous material. Synthesize and characterize it, different method the characterization. And then we follow voltammetrically the reduction of chromium 6 to chromium 3. That is a sensitivity plot, and then you will be able to find out the concentration electrochemically with this platform. Right? You have your limit of detection of the lowest concentration you can detect 8 parts per billion with the carbon-based material. Okay, how much time I have?
Sir, another half an hour.
Okay. Right. So this is another part of my talk. This basically what I'm going to talk about, the biosensing. Biosensing I'm going to talk about. That is basically a nicotinamide adenine dinucleotide and then lactate. Right? What I'm going to call is a dehydrogenase-based biosensor. Okay, right. So what we have here is this is the schematic, the fundamental of this sensor. This is a dehydrogenase-based enzyme. So how it works? I have a substrate, say for example lactate. The lactate dehydrogenase catalyzes the oxidation of lactate to pyruvate in the presence of NAD+, that is reduced nicotinamide adenine NAD+ and NADH. You have here. And if you follow the concentration of enzymatically generated NADH, you are successful in following the concentration of your lactate. So this is a little complex. I'm not going to talk about. Let me see here what we have. You need to find out the concentration of enzymatically generated NADH in order to find out the concentration of your, say for example, your lactate or glucose, whatever the analyte that you want to look at. But oxidation of NADH requires high over potential. Though the formal potential is somewhere here, these are the representative examples. That what we have here is that your oxidation takes place somewhere here. So you need a mediator to bring down this oxidation potential in order to facilitate the NADH oxidation, so that I will be able to quantify the concentration of my analyte, that is a glucose or lactate. So I need a mediator, right? Ideal mediator, what we need. So you need this. These are characteristic features, right? What we need is that these are some of the examples, right? The mediators, either you have a paraquinone or the diamine or quinone imine or your orthoquinone. See, this is some of them are potential mediator or catalyst for the oxidation of NADH. So the idea is, yeah, here is your formal potential. I want to bring it from, this is actually happening, I want to bring it down somewhere here with the help of the mediator. So what I'm going to talk about is there are two mediator I'm going to talk about in this. So those who want, you can follow this literature. Okay, this is again a Michael addition reaction. So I have a surface confined molecule, triazine type of a molecule here, mercapto-triazine type of a molecule. Now at neutral pH, this one of the proton there is a deprotonated at a particular pH, right, the neutral pH. Now once I oxidize to this one, I generate this one. On this surface, this can undergo a Michael addition reaction, and then you get a surface confined redox mediator. So I'm going to use this redox mediator to catalyze the oxidation of NADH. You can see we have done a series of molecules, series of studies, 1, 2, 3, and so on. You can see the response. I'm not good. This response corresponds to the oxidation reduction of your surface confined or adsorbed catechol that you have generated by Michael addition reaction. So now you go here. Now what you do is that you do an oxidation, because that is a first purpose. So if I'm successful in quantifying this NADH, I'm successful in quantifying my lactate or glucose. So this current, the red color one plot is basically the oxidation of NADH. The current is directly proportional to the concentration of NADH. So you can see the parameter that I have given. Response time is pretty fast, sensitive this much, and so on. Everything is given, right? Another one what we have done, again it's a playing with the molecule. So you have your carbon network here, and I want to do a chemical engineering with this one and do a electrochemical reactions. So what I do is that here I have a nitro group and then amine function. Now I convert into a diazo and I covalently couple this one with this molecule and generate this molecule. It's a complex architecture. I start with a nitroaniline and generate the diazo, and then I couple with a carbon network, so that I will be able to follow the electrochemistry of this nitro functionality by electrochemical reaction. Okay. So now what we have again, that's basically to decrease the work. I'm going to use this as a mediator. Now what I have, yeah, I do this reaction, I generate it. I'm not going to the detail. Now you see here, you have a oxidation of NADH with a redox molecule that is generated here. So you find out your concentration of NADH. Yeah, it goes here, mediated oxidation. You have here. Your sensitivity of this might limit of detection is 0.4 micromole with a pretty good response time, 21 seconds, not like the earlier one, what I have shown. Now I do the LDH, that is lactate dehydrogenase. Lactate, so the substrate comes there. Yeah, I convert into pyruvate, and then you follow this signal, and then you have a limit of detection of 2.5 micromole. That is good enough to quantify. So we have tested with the real sample, that is your clinical method as well as our biosensor, very close. This is a clinically measured. This is with our sensor. Second one, again, I'm going to talk about the same oxidation of NADH to quantify the another analyte, the lactate. So here what we have is the oxidation of NADH. Here we have a very good sensitivity. That's very important. The transducer is basically gold nanoparticle that is decorated on a silicate network. Now, what I have done is that you can see here your NADH formal potential is somewhere here. My catechol moiety is able to bring down from 0.9 to 0.2. My gold nanoparticle architecture is able to bring down to 0.05, minus 0.05. And in between that, my hydroxylamine redox mediator falls there. This is considered to be more advantageous for the actual fabrication of your biosensor that I will be showing in the next slide. So you have your architecture. What we have, these are the gold nanoparticle. These are the enzymes that is integrated inside the molecular architecture. And this is your image. Your enzymes and your nanoparticles are there. This is the reaction that I do that. And lactate can convert to the pyruvate. I follow this. This is basically the signal due to the lactate oxidation, and we follow by the current at a particular potential. So real sample analysis has been done. Now, another 10 minutes, maybe another 10 or 12 minutes, I will share you about the other kind of architecture for cholesterol biosensing. How do we do the cholesterol biosensing? So we need two different enzymes, right? What do you need? Cholesterol esterase as well as cholesterol oxidase. Because the human beings, the cholesterol content is 80% of the cholesterol is in the ester form. So what we need is that first we need to hydrolyze and then you oxidize. So you know the importance of for the measuring the cholesterol, particularly Asian people are prone to undergo a serious cardiac problem that is due to what we have, the high cholesterol content. We say that bad cholesterol or good cholesterol, low density and LDL and HDL, that and all. So you can see here, this is the less than 200 milligram per deciliter, that is desirable, borderline is here, and high risk is here, it goes here. So we have developed some of the sensors using the platforms, either silicate network or the carbon-based network using platinum and palladium-based nanoparticle, right? So what I have here is that I have a biosensing of cholesterol using a platinum-based architecture. So here, what we do is that, as I have shown here, hydrogen peroxide is followed. The first generation biosensor, those who follow earlier, here you have it. What I have is your cholesterol esterase and then is cholesterol oxidase. So you have your cholesterol ester, and that is can be converted to the cholesterol, and then cholesterol is getting oxidized in the presence of oxygen. You're generating hydrogen peroxide. So I'm going to follow hydrogen peroxide to monitor the concentration of cholesterol ester. So here what we followed is a typically simply hydrogen peroxide. I'm not going to explain all this, you can see here, with a very low detection, with a very low amount of hydrogen peroxide can be detected at a 0.1 nanomolar concentration. So here we go, right, integrate the enzyme, that is your two enzymes are inside the network, and then you follow, inject your sample and follow the signal, right? This is basically the corresponds to your cholesterol ester response by the two-step. One is hydrolysis and then oxidation by the two enzymes that's available. So we have here, limit of detection, the low concentration we could get is 0.5 micromole with a good sensitivity. Another one platform, this is little complex architecture. So here is another one platform that we have developed, carbon-based platform. You have your graphene-based platform, and you decorate with a platinum nanoparticle instead of any other nanoparticle, and then you follow the hydrogen peroxide and pretty low concentration, 0.5 nanomole of this one, and then what we did here. Right, you can see here. This is the strip that we use, the screen printed electron. So you have your platform, and you have your esterase and oxidase, and you follow the concentration of hydrogen peroxide. This is the corresponds to the real sample. That is the serum sample that we collect from the clinical laboratory. Right. Okay, so the real sample, yeah, what we have is that you have a serum 1 and serum 2. And this is the clinical method. We validate that. It's not simply measuring it. We validate it. It's very close to each other, right? The clinical method as well as our method. This is another one method that we developed instead of platinum. Platinum is quite expensive. So we attempted whether we can reduce the cost by using a palladium. Palladium is relatively cheap. I'm not saying the palladium is dead cheap. It's a relatively cheap with respect to platinum. So we developed another kind of a material, your graphene oxide-based material, and then you generate your graphene and palladium. So you characterize it, everything. Again, you do the sensing of your hydrogen peroxide. Instead of platinum, I have used the palladium. And finally, what I have here is my sensing platform for the biosensing of cholesterol. Right, you can see here, there is a real sample, serum sample, 2 serum sample, and 1 butter sample. That is just to validate whether it goes well. So commercially, this is 0.18, the cholesterol content, and what we measured is a 0.175, very close within the error limit. And this is with your clinical method for your serum sample. And finally, right, I hope that I'm very, very close to that one. Right, what we have is that another one analyte, I will briefly mention that, uric acid. Gout is a problem, right? That's a high content of your uric acid in your serum or your bloodstream, and that causes a serious problem, right? Your level, how much it should be, and so it causes a lot of serious problem whenever uric acid level is increased. Gout is basically a deposition of monosodium urate crystal in tissue. So there are methods, either you follow the first generation or second generation. Use the mediator, or the first generation you follow the hydrogen peroxide. So what I will be showing here is a redox mediator based second generation biosensor. Again, we take the carbon nanoarchitecture, covalently engineer and attach a redox molecule and characterize it, whether it is attached to the carbon network. Yes, your FTIR, XRD, and your X-ray photoelectron, everything confirms that it is attached to the electrode surface. So now you do that, you electrochemically characterize whether this ferrocene, right? You should be very familiar with the sandwich molecule ferrocene. Ferrocenium cation. Ferrocenium cation. Then we follow a little advanced. I'm not going to this one. You have a reversible redox signature. Okay. So here comes the uric acid. Right. What we do? We have this platform. We integrate the uricase enzyme in the platform and do the sensing. So here you have the signature. So in the absence of your uric acid, this signature, in the presence of uric acid, this. The current is directly proportional to the concentration of your uric acid. This is the strip that we have used, and authenticate with the serum 1, serum 2, and serum 3 also that we validate this. I think that will be the last part of my talk. That what I have here is that I will briefly share how do I sense the uric acid using a simple calorimetric method. So what I have here is that I have a molecule which is functional as the gold nanoparticle, and this is the uric acid. So I'm going to make use of the rational interaction between these two molecules and I follow the concentration of this one with the reporter, what I call is the gold nanoparticle. This is the characteristic color. With that, I'm going to follow simple hydrogen bonding interaction. So you can see here, right? You can have an interaction, hydrogen bonding interaction of this kind, or a hydrogen bonding interaction of another, right? Either your 4 molecule or your 6 molecule can undergo hydrogen bonding interaction. As a result, the individual nanoparticle can undergo aggregation and your color can change. Now, first step is synthesize a nanoparticle. Synthesize a nanoparticle that is functionalized with the thiouracil, 2-thiouracil, which can have a favorable hydrogen bonding interaction with your uric acid. And your gold nanoparticle, a wine red, it turns to be a blue color as due to the interaction between this, and then you will be able to follow spectrally. The next slide I will show you. So you increase the concentration of your uric acid. What happened is this is your transverse, your plasmon band, it decreases, and aggregation, due to aggregation, this band increases. The color changes from here to here, right? It goes here, it is 0 mole, and it gradually increase here, the color changes. You are able to quantify your uric acid by a simple calorimetric method and highly selective towards uric acid. Other analyte does not bite. So at the end of the day, what we said in a nutshell, I have briefly explained to you. I'm not sure how many of you followed it. Biothiols, yeah, mercury and arsenic, and then our lactates and uric acid and cholesterol that I have mentioned. So this is typically for the voltammetric response. We look for different signature, not simply looking into the concentration. We study the in-depth of the electrochemistry. Finally, thank you very much.
Thank you, sir. Now the session is open for discussion.
Sir, I have a question.
Yes, please. No, I can't hear. I can't hear.
You spoke about mercury.
It's not audible. It's echo is coming. Can you repeat?
Sir, spoke about detection of various analytes like mercury, right?
Hmm.
Is it possible to quantify the water insoluble dyes and the pesticides using biosensor?
Yeah, water insoluble is what we should do is that if you want to have if it is insoluble in water,
Yeah.
I mean, what we need to do is that we need to find out other method. Usually say for example, pesticides and the herbicides and all, there are methods are available to solubilize it and expose to the solid state sensor.
Yes.
Otherwise, we need to go for a solid state method that may also be available. Physics people handle that kind of a solid state method, but conventionally used is that, yeah, so to take the soil, the pesticide or herbicide, whatever is there in the soil, take the soil and transfer to the solution, either it's a non-aqueous or aqueous medium, and then use your strip to find out the concentration. That is a routine method. Usually agriculture people use the same method.
Okay, sir. Thank you, sir. So I have another question.
Mm-hmm.
See, the colloids are basically carrying the contaminants, right?
Pardon, what is that?
The colloidal particles,
Mm-hmm.
nanoparticles, they carry the contaminants, right? Because they have the adsorption capacity.
Yeah, not necessarily cation. It can be cation or anion, which will be stabilized.
Yeah. Okay. Thank you, sir. Thank you.
Okay, there is no more question. We thank
No,
you,
no,
sir,
so just
for
hold
your
on.
valuable information.
Yeah, just hold on. Right, if the students are there, students should interact. The sole purpose of spending my 1 hour is to interact with the students. Right, I expect that the students are there, they ask question, not necessarily related to what I talked about. In general, about the chemistry, general. That's the sole purpose of coming online here.
Sir. Sir, what about the solubility of nanoparticles in biosensors?
The solubility of nanoparticle is colloidal nanoparticles should be prepared in aqueous solution, and these are all very nano. I mean, 2 to 3 dimension and are not. So I mean, using that as a different purpose inside the body in vivo, that's totally different. So what I talked about is the in vivo biosensing. So there is no problem. You don't need to solubilize. It is basically on the surface of the electron, or it is in the solution where you bring your analytes. So there should not be any problem at all. If you're talking about this nanoparticles in vivo, whether it is biocompatible.
Okay, thank you, sir. Dear students and dear participants, you can ask some more questions.
Okay, thank you.
There's no more questions. I thank you, sir, for your valuable information, sharing your research findings and ideas with us, and spending your precious time. Thank you, sir. So, showing gratitude is one of the simplest yet most powerful things humans can do for each other. Now, I invite Aditya Venu, second MSc Chemistry, to deliver the vote of thanks.
Good morning to all. I'm Aditya from second PG Chemistry, and I have to convey thanks to all faculties and students who have participated in this webinar. First of all, I convey my thanks to our head of the department, Dr. Murali sir, who have addressed the welcome speech in this webinar. Thank you very much, sir. And also thanking to Sheba ma'am for coordinating such a webinar for us. Finally, I'm thanking to our speaker, Dr. C.R. Raj, Professor of Department of Chemistry at IIT Kharagpur, who have conducted a beneficial and useful seminar about functional materials and molecular assemblies for the sensing of bioanalytes and water contaminants. It's a very useful seminar. Why I'm saying like so? Because most of the contributions of science field, especially in chemistry, to our public is more relevant in everyday life. Yes. But it is equally important to accept the truth that we are the chemists responsible for accumulation of waste and contamination of water in the environment. So it is the urgent need of the time to carry some research in the field of waste management and natural sources, because all of the pros and cons that are affected by the public, and we have the responsibility for such a condition. And in this scenario, such a useful seminar is a definitely delightful pathway to upcoming research students for the nation's sustainable development. So thank you very much, sir, for such a wonderful webinar. And thanks to all the faculties and students who have participated in this webinar session. Thank you, sir. Thank you very much.
Thank you, Uneda. You can fill the feedback form for getting certificates. Thank you all.